static int L1 equals 0x01234567 semicolon. Okay? But it's a very rough approximation. Because the way, okay, let me just write this so that you can see what I'm talking about. Okay. Okay, so only for this class we can kind of, sort of, maybe look at it this way in C. Okay, so in C it's kind of like static int L1 equals 0x123456 semicolon. Okay. The static is here because this particular label, because it is not it's not a dot global, it means it is staying within only this particular source file. In C and C++, when you have a global variable without a static, it is by default exposed to the linker. If you use the word static before the definition of the variable, it stays, it is still global within that particular source file, but it is no longer visible to the linker. Other files cannot see that anymore. And that's the effect of the static. Int is kind of dangerous because it depends on whether you're using a compiler in 64-bit mode, 32-bit mode, or 16-bit mode. So I'm taking a risk here to call this an int because int is not necessarily 32-bit, but I'm making that assumption here. Equal to means it is an initialized variable, and then the hexadecimal number is identical to the one that we are using here. So it has a similar effect. But the way you should look at it is not to look at it in the C way, is to just look at it from the assembler's perspective, which is nothing more than I'm allocating 4 bytes, and these 4 bytes together will represent the value 0, 1, 2, 3, 4, 5, 6, 7 in hexadecimal, and no more, no less. Okay? In other words, when you do this in assembly, nobody's going to give you a warning if you just access 1 or 2 bytes out of these 4 in the wrong order at the wrong location. Because every byte is equal, okay? You don't have to start with label L1. You can start with label L1 plus 1. There's nothing wrong with that. Or the assembler would not complain about it. Okay. This instruction here is kind of, for this class, the same as EAX equals L1, using the same using the same example here. It is actually going into memory, go to the location, grab those 4 bytes, and copy that to the register EAX. Now there is no equivalent of a register in C and C++, so I'm keeping the percent symbol to emphasize that EAX is a register. It's a register getting changed. Are we still doing okay so far? The next instruction is kind of doing this. It's kind of saying EBX is getting the address of L1. Okay, because we're putting a $ in front of L1, which means whatever L1 is, okay, the label L1, whatever it is, it specifies the bit pattern that will be copied to EBX. Now, in this particular case, L1 so happens to be the address of something. So you're effectively copying the address of something into EBX. Yep.
So it's when you say $L1, it's not arbitrarily evaluating the characters L and 1 and trying to derive a number out of that?
No, it is not doing that.
Okay.
It is looking at L1 as one particular label. It goes through its own symbol table to find out how L1 was defined.
Okay.
Right.
So $L1 might result in some different random compilation of numbers on a different machine, or would it always be the address of?
No, it does. It's not necessarily the address of something. Okay, let me give you another example here. So I can have an L2 here. So this will break the our understanding of this stuff. Okay, so we'll have an L2 here, and I'll just define L2 to be whatever. Okay, a particular number. Okay, just random number. So we can. So in this case, we can't use the equivalence anymore because when we say move L2 to, let's say, ECX, ECX equals L2. It's not that anymore because there is no such variable L2. L2 is nothing more than an entry in the symbol table that tells the assembler every time you see L2, it is the same as, that particular number. It just so happens that L1 was defined to be an actual address that we can sort of borrow the concept of variables from C and C++. But in general, we cannot.
Okay.
Are we doing okay so far with this? Because the differentiation between immediate and direct operands is extremely, extremely important. Yep.
So, you said $L1 is an expression, and so if you
L1 is an expression.
Okay, so could you like add 1 to that and multiply it over?
Absolutely. You can
Okay.
do anything you want. Okay? So if I go back to this program, I can say, in this case, unless I have L1 and L2, I can do something that's, I don't know why I would want to do that, but I can. I can do that. It's not a problem. To the assembler, what is happening here is, after the dollar symbol, it's just expecting an expression of some kind that evaluates to a 32-bit integer. Or I should just say 32-bit pattern. That's all it's expecting. Okay. So in this case, what it's going to do is it will find out how L1 is defined. L1 is the address of something, okay, but it has a value, right? Every address is an integer, it's a 32-bit value in the 32-bit architecture. So it will take this it will subtract L2, which is defined to be this number, from L1, which so happens not this number here, but the address of that number, okay, the number that we saw earlier in the debugger. Whatever the difference is becomes this value. We multiply that whole thing by 2, and then whatever the product of this entire thing is, we'll divide it by 23, and that becomes the bit pattern that is going to be copied to register EBX. Does it access memory? Does it go to memory and go, oh, I'm going to grab these 4 bytes and copy that to EBX? No. The answer is no, it does not, because it's an immediate operand. Okay? What if I have an instruction like this? Move L2 to EDX with a dollar symbol. This is not EDX equals the address of L2, because once again, there is no variable L2 in this case. L2 is nothing more than a label defined to be a certain value. But it does not, in this case, L2 does not correspond to a memory location that is meaningful to me. Okay? So this one is really just copying the value of L2 into register EDX. So are we doing okay so far? Without the dollar symbol, that's an extra step of going to the memory location to copy it, or to copy to. With the dollar symbol, it does not access memory. Yep.
You said L1 is a 32-bit value, right?
Every label is 32-bit.
Where is that number stored?
It is stored while the assembler is running.
So where? Inside the CPU or some register?
It's inside the symbol table of the assembler when it runs. So it's a transient construct that is present when the assembler is interpreting this program. Now, if you turn on debugging, not debugging, but if you include the symbol table, which is G-steps, it will also be stored in the object file. And when you link, object files with symbol tables already defined, the executable will also be included in that symbol table. In fact, that may be something that we can take a look at. Yep, go ahead.
Oh, yeah. Could you add a number to the first one, L1?
Absolutely.
And would that move it by byte?
It will change, yes, it will be moving by bytes. Okay, so let's go ahead and, look at what you just said, okay? Instead of adding 1, I'm going to do subtract 1, okay, just to make it more fun, okay? What would be the equivalent instruction in C? In this case, there is an equivalent because L1 is kind of like a variable. It is corresponding to a memory location. It is no longer something simple in C. let me move those two instructions side by side, or right next to each other, so that this way we can compare and contrast the two. This one, if you want to really see what it looks like in C, it will look like this. Okay. Now, first of all, we have to do the subtraction of the address, right? So you have to say, okay, the address of L1 minus 1. But that doesn't work because L1 in C and C++ has a type associated with it, and in this case is an int. So when you subtract 1 from the address of an int, you are actually changing the location by 4, because this is a 4-byte thing. So subtracting 1 is subtracting 4 bytes of address, because you are subtracting 1 item location, but 1 item is taking up 4 bytes. So when you're looking at byte address, you're actually subtracting 4. So what we need to do first is to cast it to a char pointer first before we do the subtraction. So let me just use extra parentheses so that we emphasize the order of operation. After you subtract 1 from that thing, the entire thing becomes a char pointer too. So we cannot, we don't want to dereference a char pointer, so we have to recast the whole thing as an integer pointer. Okay? And after we recast the whole thing as an integer pointer, we can now do the dereference. Since you guys have all passed 360 with a letter of grade of C or better, this should be familiar. I'm just kidding. But but this is what it means. Okay, this is what it means in C and C++, and that's why I don't want to look at it from the perspective of C and C++, because it is a very rough approximation of what the assembly representation is really saying. Okay, but this gives you an idea of the differences between the two languages. And even though sometimes we can kind of borrow operators and meanings and words from C and C++, in general, it's not a very good idea to do that. Are there any questions at this point? No? Is this confusing, or are we making progress?
I'd rather just forget the whole C and C++ nonsense altogether. It was clear.
Yeah, it's kind of hard to undo that, especially when you have other classes that require that knowledge.
I mean, just for assembly language standpoint.
Yeah.
You can go back to it later. But
That is correct. I would definitely support that decision. It's not to look at things in terms of C and C++, but in a much lower level term from the perspective of the processor. Yep.
So the second line, L1 colon and dot int, is that dot int simply saying?
We are allocating things in 4 bytes as a chunk. So tell me what those things should represent.
Okay.
That's basically what dot int is saying.
Memory location.
No, not memory location. The value at those memory locations.
All right.
Okay. Well, maybe we can go to the debugger again and take a look at things and.
there's a comma you need before you try to run that.
Sorry?
There's a comma you need before you try to run that.
There's a comment that have to.
L2 ECX, move all L2 ECX.
Which line?
12.
12. Oh, I'm missing a comma. There we go. Okay, thank you. Actually, I'm going to do this. I'm removing the comma just to see what kind of error message I get. Now, this is another thing that you can do is intentionally trying to introduce errors so you can see what error message you should be getting.